In this presentation, I am going to explain analysis of DC electric circuits using mesh current method, and this is for first year BTech Basic Electrical Engineering course. Now let us see Kirchhoff's voltage law KVL that is required for the mesh current analysis. The KVL Kirchhoff's voltage law is defined as the algebraic sum of all voltages in any closed circuit or mesh or loop is equal to 0. Meaning that the sum of the EMFs of voltage sources and the sum of voltage drops or rise in the circuit element is in a closed circuit is 0 at any instant of time. Now coming to the circuit, a closed circuit here, there are 1, 2, 3, 4, 5, 6, 7 resistive element is there, 1 voltage source is there, and here we are going to apply the Kirchhoff's voltage law to this loop, KVL to this loop, and we are assuming the current direction in a clockwise direction, and we have to assign the voltage polarity. Normally, in a resistive voltage drop here, what we are assuming that the point where the current is entering that element is taken as positive. Therefore, that is why here it is taken as positive and here minus. Again, here plus and minus like that. Voltage polarity is marked. Then we are going to apply the Kirchhoff's voltage law. Starting from here, the voltage, if you starting from this direction, here plus to minus, the voltage drop is there. Normally, the voltage drop is taken as a negative and voltage rise is taken as positive. While we are writing the KVL equation, the voltage drop is taken as negative and voltage rise is taken as positive. Therefore, coming to this loop, the circuit here, electric circuit, here the drop is equal to minus V1. Since it is a voltage drop, we are taking minus V1. Again, here it is equal to minus V2, then minus V3, then minus V4, then minus V5, then drop minus V6, then this drop minus V7. Then coming to this, here if you proceed like this one, it is plus to minus, it's a potential, sorry, minus to plus, it is a potential rise. That is why plus V8 equal to 0. Therefore, this equation is, if you rearrange here, V8 equal to V1 plus V2 plus V3 plus V4 plus V5 plus V6 plus V7. Therefore, this is the Kirchhoff's voltage law equation for this loop, and that is here. These are the voltage drop is that is the falling potential comes in the resistive case, plus minus the voltage drop, fall in the potential. This is also falling potential. Here all there is a falling potential is there, but across this voltage source there is a rise in potential. Therefore, the algebraic sum of the potential across this one, that is falling potential is taken as negative and rise in potential is taken as positive, and the algebraic sum is equated to 0. Then we'll be getting the voltage source equation, that is VA equal to V1 plus V2 plus V3 plus V4 plus V5 plus V5 plus V6 plus V7. Therefore, this is the KVL Kirchhoff's voltage law applied to this electric circuit. Therefore, this is required for the mesh current analysis. Now let us see mesh current analysis. In mesh current analysis, usually called mesh analysis, always the number of unknowns, here it is the unknowns or currents, will be equal to the number of meshes. That is, here the circuit is shown here. It's a very simple circuit in which there are two meshes, mesh 1 and mesh 2 is marked. Here resistance R1, R2, R3 and the two voltage sources V1 and V2. This is a two mesh electric circuit here, and the mesh analysis is a method of circuit analysis using mesh currents instead of branch currents, as in the case of KCL or KVL method. That one, currents in KCL, KVL, that is instead of branch currents in KCL and KVL method. Here we are using mesh current. We are assuming this current mesh, we are mesh current IM1. Similarly, this mesh, second mesh current IM2, like that one. And once we calculate this mesh currents, you can calculate what is the branch currents in terms of this mesh currents. For in this case, the electric circuit, there are two meshes, and this is called the mesh 1. This is the mesh 1, and this one, that is, this is a mesh 2. The two meshes are there, and there is a one element which is common to mesh 1 and mesh 2. That is, R2 is common to mesh 1 and mesh 2. Therefore, here, in order to calculate the branch currents in terms of the mesh current here, the current flowing through this resistance R1, that branch current I1, is same as the mesh current IM1. I1 equal to IM1, since the current I1 is the same direction as IM1. Similarly, here the current I3, this branch current I3, that is current flowing through the R3, that is equal to the opposite to the IM2, that is second mesh current IM2. Therefore, that is equal to minus IM2. For I3 equal to minus IM2, since the current I3 is in the opposite direction of IM2, that is why the branch current I3 equal to minus IM2. Then next one, this branch current, see I2, that is equal to, if you are assuming I1 is more than IM2, we are considering, since it is marked as I1 in this, I2 is in this direction, that is equal to IM1 minus IM2. IM1 minus IM2, since I2 is in the same direction as IM1 and opposite to, and it is opposite to the current direction of, opposite to direction of IM2. That is why that is the current I2, which is equal to IM1 minus IM2. IM1 is the loop 1 current and IM2 is the loop current. The difference of that one is the branch current I2. Therefore, this is the mesh 1 and this is the mesh 2. Coming to the mesh current analysis, what are the different steps involved? First step is that identify the meshes in the given circuit. For example, this is a electric circuit in which the two meshes are there, mesh 1 as well as mesh 2. For identify the meshes in the given circuit, a closed loop that does not contain any other loop within it is referred as a mesh. Therefore, this is a mesh 1 and this is another mesh 2. Step 2, that is same circuit is shown here. That is marked as, this is the mesh 1 and this is the mesh 2, and the mesh current is marked as I1 and this mesh current is, second mesh current is marked as I2, R1, R2, R3. These are the voltage sources V1 and V2. Second step is that assign the mesh current I1, I2, I3 in the clockwise direction. That is the mesh current I1 in clockwise direction, mesh current I2 in the again the clockwise direction. Step 3 is assign the voltage polarity for all the circuit elements except the voltage sources. Therefore, here the voltage polarity is to be marked here. In this case, I am assuming that the point where the current is entering is taken as plus. Therefore, this is plus and minus, since the I1 is entering this point, resistance R1, this is plus and minus. Similarly, here also we can say that I2 is entering at this point, that's why it is plus and this is minus. Therefore, that is why in this case we are assuming here the first mesh here, the current I1 is flowing here and the second mesh current is flowing, I2 is like this one. So the net current in this direction equal to I1 minus I2. In that case, the voltage polarity in this side plus and minus is taken for the mesh 1. But coming to the mesh 2 here, the mesh current I2 is I2 in this direction, I1 is in opposite direction. Therefore, if you are assuming the net current in this direction, that is I2 minus I1 in this direction, here plus polarity and here minus polarity across R2. Therefore, for the mesh 2, for this element, voltage polarity is plus here and minus here. For mesh 1, this voltage polarity for this same element plus here and minus here while writing the Kirchhoff's voltage equation. Now, these are the two voltage sources V1 and V2. Therefore, in resistive drop, the point where the current enters is taken as a positive. Therefore, here plus here minus, here plus here minus, and in this side plus here and minus, because I1 minus I2 is entering here, and in this case I2 minus I1 is entering here, that's why plus here and minus here. Therefore, the voltage polarities are marked here. Now, continuing the mesh current analysis, the steps involved. The fourth step is that write the Kirchhoff's voltage law equation in all the meshes with assigned voltage polarity in the clockwise direction. Because already we have seen that voltage polarity we are already assigned. Then Kirchhoff's voltage law is applied to the each meshes. For example, the mesh 1, if you are applying the KVL to the mesh 1 here the drop is there, that the corresponding drop, and here also voltage drop, and here the potential rise is there. Therefore, if you write the KVL equation here, V1 that is the voltage V1, then here the drop is equal to I1 into R1 minus I, because drop minus I1 into R1. Again, this is also drop. Therefore, I1 minus I2 is the current through this direction or through the resistance R2. Therefore, minus I1 minus I2 into R2 minus I1 minus I2 into R2, that's equal to 0. Therefore, that is the first mesh equation. Similarly, we have to apply the Kirchhoff's voltage law equation to the second mesh here. In this case, here current through this one is, that is I2. I2 drop is that minus I2 into R2 minus I2 into R2. Of course, this current is equal to I2 minus I1 in this direction. Therefore, I2 minus I1 into R2. That, of course, since it is a drop, it is minus. Minus I2 minus I1 into R2. Then here also drop. Minus I2 into R3. Minus I2 into R3. Again, plus minus a drop here. That is why minus V2 equal to 0. Therefore, this is the second mesh equation. Therefore, we have got mesh 1 equation and mesh 2 equation. Only two unknowns, the mesh current I1 and the mesh current I2. We can solve these two mesh equation and can calculate what is I1 and I2. Once we calculate the mesh currents I1 and I2, the branch currents can be calculated. For example, the current flowing through this branch equal to same as the I1, and current flowing through this branch is same in this direction, it is same as I2, or in this direction it is equal to minus I2. Therefore, the current flowing through in this direction equal to I1 minus I2. Therefore, after calculating the mesh currents, we can calculate the branch currents. For the steps 5, solve the KVL equation to find out the unknown quantities, that is mesh currents I1, I2 in this 2 loop. If it are n loop, up to n, in can calculate. The step 6 is that compute the required quantity of branch currents from the mesh current. As I told you, this current, the branch current is same as I1. This branch current is same as I3. And this branch current is same as I1 minus, this branch current is same as I2. And this current is same as I1 minus I2. Like that, branch currents can be calculated once you get the mesh currents. Now let us see an example problem. Calculate the current through the resistor R2 using the mesh current analysis in the following circuit. Circuit is given here. There are two voltage sources, like here 28 volt source is there, and this is the 7 volt is there. Resistance R1 4 ohm, R2 2 ohm, and R3 equal to 1 ohm. Therefore, by the simple circuit, the question is that what is the current flowing through this resistor? That is to be solved using the mesh current analysis. First, we have to identify what are the meshes. In this case, this is a one mesh and this is a second mesh. Therefore, identify the mesh 1 and mesh 2. That is the first step. Identify the meshes in the given circuit. This is the mesh 1 and this is the mesh 2. Now, continuing the same example. Second step is that after identifying the meshes 1 and 2 here, next one, assign the mesh currents. That is, this is the mesh current I1 and this is the mesh current I2. That is assigning the mesh currents the clockwise direction. That is, this is the current is identified as the clockwise direction. That's the second step. Third step is that assign the voltage polarity for all electrical element except the voltage source. Except the voltage source. We can say that for except voltage sources, we are assigning the voltage polarity for all other circuit elements. And in resistive drop, the point where the current enters is taken as positive. Therefore, the current is entering that point is taken as positive. For example, in this case, the mesh current is I1. Here the current is entering. That is why plus marked here, minus marked here. Similarly, here, this is the current I2 that is entering this point. That is why plus here and minus here. And if you take this one, the common element or common branch for mesh 1 and 2, here if you take the current I1 is in direction and I2 is in opposite direction. If you assume the current in this direction for the mesh 1, I1 minus I2 is the current that is entering. That's why here we are taking plus here and minus here. For the second loop, if you take the current I2 minus I1 is the current in this direction, that since it is entering at this point, here plus and minus, and this current is equal to I2 minus I1. Therefore, we are marking the polarities of this voltage drop. Then next step is that write the KVL equation in all the meshes. That is, all these two meshes, we are writing the Kirchhoff's voltage equation with assigned voltage polarity in the clockwise direction. We are writing the KVL equation in the approaching the clockwise direction. Therefore, applying the Kirchhoff's voltage law equation for the mesh 1, we are moving in the clockwise direction. What is the voltage drop here? What is the voltage drop here? It is equal to the I1 into 4 ohm. Therefore, since it's a voltage drop, we are taking it as minus. For minus 4I1. That is why it is called minus 4I1. And here, if you see that one, first one, the voltage source, that is equal to 28 volt. Therefore, if you clockwise direction, if you proceed like this one, here minus and here plus, say potential rise. That is why it is plus 28. For plus 28, the drop here is equal to minus 4 ohm into I1, minus 4 I1, mesh current I1. Again, the drop here is equal to, the resistance is equal to 2 ohms. Therefore, minus 2 into I1 minus I2. The net current in this direction equal to I1 minus I2. Therefore, this is a drop it is there. That is why minus 2 into I1 minus I2, minus 2 into I1 minus I2 equal to 0. Or if you are rearranging, we'll get 6I1 minus 2I2 equal to 28. That is the mesh 1 equation. Similarly, we apply the Kirchhoff's voltage law equation to the second mesh here. Applying KVL to the mesh 2 here. Here again, the current flowing through in this, you have to move in a clockwise direction. Therefore, here the current is entering equal to, in the second mesh, it is equal to I2 minus I1. Of course, the R2 is the resistance. So, therefore, since the drop, it is equal to minus. Therefore, minus 2 I2 minus I1. Minus 2 I2 minus I1. Then drop here equal to, again, minus 1 ohm resistance and into I2. Therefore, minus 1 into I2, or minus, it is equal to minus 1 into I2. And here it is equal to plus and minus, drop is there, it is equal to minus 7 equal to 0. Or it is equal to 2I1 minus 3I2 equal to 7. Or that is the second mesh equation. Therefore, the two mesh equations, and we can solve this two mesh equation or this KVL equations, and we can get the unknowns I1 and I2. Now we are converting those mesh equations into in a matrix form, like it is equal to 6I1 minus 2I2 equal to 28. Then 2I1 minus 3I2 equal to 7. These are the two equations, and this is a coefficient matrix. This is the current column matrix, and this is a voltage or the voltage source, that is a column matrix. Then unknowns are I1 and I2. And this I1 and I2 can be solved by this matrix by using the called Cramer's rule. Cramer's rule here, the unknown I1 equal to the determinant D1 divided by D. The determinant D1 by D equal to, where D is the determinant of the coefficient matrix, which is equal to determinant 6 minus 2, 2 minus 3. That is D. But to get D1, the first column is replaced by this voltage, that is 20 voltage vector, or 28.7. Therefore, it is equal to 28.7. Second is same, minus 2 minus 3. And then already I told you, this is the determinant of this coefficient matrix. And then determinant is calculated, 28 into minus 3 minus 7 into minus 2. Similarly, this is also be calculated, that is 6 into minus 3 minus 2 into minus 2. And then ratio is taken, then we'll be getting 5 amperes. Therefore, the current I1, the mesh current I1 is calculated as 5 amperes. Similarly, we can calculate the mesh current I2 again using the Cramer's rule. I2 equal to D2 divided by D. D is same, that is the determinant of this coefficient matrix, that is determinant 6 minus 2, 2 minus 3. And the numerator D1 is, D2 can be obtained by I2 equal to D2 by D. Or D2 can be obtained by the replacing the second column by this voltage vector, or that is equal to minus 2 and minus 3 is replaced by 28 and 7. Therefore, it is equal to 6 to 28, 7. That is in matrix, that is the determinant of that one. That divided by determinant of 6 to minus 2 minus 3. Or if we are getting the determinant of this one divided by the determinant of D determinant, we will be getting the ratio which is equal to 14 by minus 14 by 14, which is equal to 1 ampere. Therefore, the mesh current here is equal to 1 ampere, and this mesh current is equal to 5 ampere. The question is that what is the current flowing through this 2 ohm resistor, which is equal to I1, the mesh current I1 minus the mesh current I2. Therefore, the current flowing through the resistor R2 equal to I1 minus I2, which is equal to 5 ampere minus 1 ampere, is equal to 4 ampere. Therefore, the current through this 2 ohm resistor, which is equal to I1 minus I2, equal to 5 minus 1, which is equal to 4 amperes. Now let us see another example. Find the current through the 3 ohm resistor using the mesh current method. Same method as I already explained that one. And here this is the same 2 mesh circuit in that one. We have to write the mesh equation as we have seen. Looking into this one directly, you can write it. You can mark the polarities of the voltage drop here. Since the current is a clockwise current, always we have to take the current, the mesh current in the clockwise direction. Therefore, this is the mesh 1 and this is the mesh 2, and the drops are marked here where the current is entering plus and leaving minus. Here plus and minus because what we are assuming here current is equal to entering current equal to I1 minus I2, and here the current equal to I2 minus I1. That's why plus here minus. Therefore, as we have already seen, we are writing the KVL equation for the mesh 1, and which is equal to, that is here the drop is equal to minus 6 into I1, then minus 3 into I1 minus I2, then here potential rise plus 42 equal to 0, or 9 I1 minus 3 I2 equal to 42. That is the first mesh equation. Second, applying the KVL to the second mesh, we can get it is equal to, which is equal to the drop here, that is why minus 4 into I2, minus 4 into I2. Then this is also a drop, that is why minus to plus. If you are proceeding like this one, this is minus and plus. It's a potential rise. As here in this case, it is equal to potential rise. That is why it is plus it is taken. Since it is the, if you proceed like this in a clockwise direction, it is minus and this is plus, is a potential rise. That is why it is taken as plus 10 volt minus here potential drop, which is equal to 3 ohm or 3 into current equal to I2 minus I1, or minus, since it is a drop, minus 3 into I2 minus I1 equal to 0, or it is equal to 3 I1 minus 7 I2 equal to minus 10. Therefore, we have got two equations, mesh equation 1 and mesh equation 2. We can solve these two mesh equations and get the unknowns, mesh currents I1 and I2. From that, we can calculate the branch currents, what's the current corresponding to 3 ohm resistor equal to I1 minus I2. Therefore, we are writing the corresponding in a matrix form, the equations. This is the coefficient matrix is given by 9 minus 3, 3 minus 7. That's the coefficient matrix, this one. That into the column matrix, the loop the mesh currents I1 and I2, and that is equal to the voltage, column matrix, like it is equal to 42 and minus 10. Therefore, we have to, this is the corresponding matrix equation relating the current, mesh current I1 and I2, and the corresponding the elements value, that is 9 minus 3, 3 minus 7. It's a coefficient matrix, and this is the column voltage matrix. You have to solve for I1 and I2, that is the mesh current I1 and the mesh current I2. Now continuing the same example here, as we have seen, this is the matrix, coefficient matrix into I1, I2. It's a column matrix, current source in the current mesh, the current values of the mesh 1 and mesh 2, and this is the 42 minus 10, the voltages. And we have to find out what is I1, that is the mesh current I1, and what is the mesh current I2. As using the Cramer's rule, we can find out I1 equal to the determinant d1 by d, where determinant d is the coefficient matrix of determinant of this one, 9 minus 3, 3 minus 7, 9 minus 3, 3 minus 7, and this d1, in order to get this matrix, this determinant, you have to replace the first column by this voltage vector, like 42 minus 10, 42 minus 10 minus 3 minus 7. Therefore, this is d1 determinant, and this is d, or this, take the ratio of that one. Therefore, 42 into minus 7 minus 10 into minus 3, and in the denominator 9 into minus 7 minus 3 into 3, and we'll be getting it is equal to 6 amperes. Therefore, the mesh current 1, that is I1 equal to 6 amperes. Same fashion, the mesh current 2 is to be calculated. I2 equal to d2 by the determinant d2 by d, where determinant d is already we have seen what is equal to the determinant of this one, determinant of 9 9, 3, minus 3, minus 7. And to find out D2, replace the second column by this voltage vector. So minus 3, minus 7 is replaced by 42 and minus 10. Then it is become 9, 3, 42 and minus 10. Calculate the determinant here. 9 into minus 10 minus 3 into 42. Similarly, here 9 into minus 7 minus 3 into 3, or the ratio is equal to 4 amperes. Therefore, the mesh current, second mesh current equal to 4 amperes. The first mesh current I1 is equal to 6 amperes. Therefore, the current through this common branch, which is equal to I1 minus I2, which is equal to 6 ampere minus 4 ampere, that is equal to 2 ampere. Like that, after calculating the mesh currents, you can calculate the branch currents. In the next presentation, I'll be explaining the circuit with current source. In this case, there's no current source, but I'll be explaining the circuit that contains the current source. How can we solve by using this mesh current analysis? How can we solve for a circuit containing the current source? That will be explained in the next presentation.